Well, here we are, our last day of 102. Let me start with some announcements. In fact, let me start with some announcements about the final. Can you go down to the pad here? Well, that might be difficult because I guess we're set up for this demo. You want me to, if you want, I can, yeah, there it comes. Sorry, I forgot about that. Yeah, so I guess the final is next Tuesday at 8:30. I think it's in Terman Auditorium, but we'll verify that. So in other words, we're gonna have lots of room and stuff. And the decision has been made that it will be open notes. So just bring all your notes, whatever you like for 102, and I don't know. That'll just make it easier. That way, you can. It won't be for missing a formula or something like that. Anyway, the problems aren't like that so much anyway. So it's open notes, but it means you won't have any problem because you're missing some formula or the stability conditions for a third order polynomial or something like that. You can just look it up. Okay, so there's probably not much more to say about that except there's a review session Sunday, right? And details will be forthcoming. So probably not much more to say about that. And we'll post the solutions for homework 8 is the one you're handing in today, right? Like tomorrow or something, or we'll have them available tomorrow or something. Maybe this afternoon, maybe tomorrow. Okay. Today, otherwise, we have a kind of a weird hodgepodge of different topics. The first is to finish up these demos, all of which were built by Leo. So maybe the first thing for you to do is to pan this way, and we'll actually take a look at a real phase lock loop. So that's this little guy. There we go. And you'll want to actually both of these are PLLs, but you'll want to make. I don't know how far is that. Are you at your zoom max? There you go. Okay. So this little guy here, once it comes into focus, there we go. There's that's a phase lock loop. It's an integrated phase lock loop, and in fact, even the size of this thing is misleading. An actual phase lock loop is typical size would be on the order of 1 millimeter by 1 millimeter, something like that. So, see that? That's mostly just packaging. Okay, so that's a phase lock loop. It's a famous one. It's called it's a 565. And I guess they've been making them for maybe 15 years or something like that. And sure enough, it's pretty much what we have in the lecture notes. And I don't think we ever got around to having any homework problems on phase lock loops. But it doesn't matter because it's just basic. It's just basic elementary feedback. So it's pretty much exactly what you saw in the lecture notes, or it's like stuff you've done in the homework. Leo has set this up now so that we have an oscillator which drives it. That's going to be our omega in. Let me go back to the figure here. I'm sorry about this, but maybe if you could just pan over here, and then yeah, there you go. Okay, so here's our PLL figure here. So we have an oscillator hooked up here to provide our input frequency. We'll see that in just a minute on the oscilloscope. There is this little integrated circuit contains a phase detector, which is in fact more or less like the phase detector in the notes. In other words, it's quite like the phase detector in the notes. The loop filter here I think is first order, but I'm not actually sure. We're not going to do enough of the demo that it's going to make a big difference. It is first order, in fact. So, in fact, this is exactly like the notes. And let's see, that's about it. So this is the block diagram. For this one was set up so that the free running frequency is around 95 kilohertz, something like that. And the lock range is about plus minus 15 kilohertz. That's actually a considerable range. More than you would normally have. Most PLLs actually do their work with a lock range that's plus minus 1%, or in some cases, way less, like plus minus 0.01%. And so that's this is for I don't know what type of applications actually require plus minus 15%. I can't actually think of any. but obviously they exist. So let me show you a little bit, actually, before we actually look at the demo, let me just show you a little bit about how this, how this works. The details here aren't important, but here's the 565 phase lock loops, an integrated phase lock loop. And here's a picture, for example, of the pinouts. And all the parts, I don't know how close you can zoom in there. We're probably pretty much at the range here. Wow, okay. So in fact, all the parts are there. There's your phase detector right there. There's your VCO. And the amp is, in fact, our G of S. It's nothing more. So it's all here. And you have connections to various of the various types of pins here. For example, by choosing the timing capacitor and the timing resistor, you set the free run frequency. You also have things by changing in this amplifier the feedback connection, that's between 6 and 7 here, you can actually change the transfer function G of S, literally. That's exactly what you're doing. So you can have a first order filter, you can have a ninth order filter if you like. It's perfectly, that's your choice. It depends on what you connect between here, here, and here. Here you have things like the phase comparator, VCO input, VCO output, and so on, and the power supply connections, negative and positive. So that's it. That's the 565. In fact, Leo hooked up a much more fun demonstration where he had 2 of these running. And in the first one he used as a VCO, he used only the VCO, and you could put in a signal, which would then frequency modulate this thing, which the other would lock to. But we don't have time today because I want to do there's just a few review things I want to do. So we won't have time to do the fun demo. That explains why there's actually 2 PLLs on this little proto board here. Okay, so that's the picture. And just for fun, I thought I would, you can go through and you'll actually find in the spec sheet, you'll find everything here. You'll find, for example, what KOS and KDET are. You'll find out how many volts per degree error you get. All sorts of stuff like that. Here you go. Here's one. Here's, for example, KOS is precisely 6,600 hertz per volt. Okay? So there's your VCO sensitivity, and so on and so forth. Okay, so let me actually show you, just for fun, what the schematic is, if you're curious. Okay, so if you go down, there you go. Yeah, you might want to zoom out a little bit to get the whole thing. So there you go. There's a whole phase lock loop. Actually, what we've decided to do is base the entire 102 final exam around this. It might look imposing to you now, but I promise by the time you finish 113, actually I can't say that because some of you probably have finished 113 and it still looks imposing. Isn't that true? But are any of you here? I can get away with it as long as no one's here. All right. As soon as you finish 214, let's say, it won't look imposing to you anymore. Actually, come on, if you've seen 113, then already parts of this are beginning to make sense to you, I'm sure, right? Like, I don't know, little biasing current mirrors, little differential pairs right there with feedback right there. There you go. There's 113 and 102. So this looks scary, but it's not anywhere near as, by the time you've taken another class or two, you'll be quite fluent in this. But anyway, I thought you just might like to see. That's what a PLL is. Actually, the really good news is that, in fact, what's really so great about all of this these days is that this doesn't make any difference at all. It's like computer architecture. Other people work on it. So you can use PLL. So the number of people who use PLLs, in particular, use this PLL. The ratio of that to the number of people who actually know how to design one is maybe 1,000,000 to 1. Okay, so 1,000,000 people. There's really just there's not that many people in the world that know how to design a PLL like this. And for every one of them, there's zillions of people who use them. And my suspicion is that most people here would be in that category. Certainly I know how to use one, and I could design one, but it sure would take me a long, long time. And it probably wouldn't work anyway when I finish it. So, okay. All right, that was just for fun, just to let you know what a PLL looks like. And at the block diagram level, it is very, very close to it's very, very close to the description I have in the lecture notes. In fact, the description in the lecture notes is kind of based on the 565 because that's kind of a classical PLL. Okay, so let's see how it works, or if it's currently working. Maybe if you go down to the oscilloscope, so we'll let our look for our. There we go. There it is. Okay. Yeah. Oh, okay. Refocus. And so let me explain what you're seeing here. So the bottom trace here is the output of the VCO in the in the PLL. The top trace is the input which we are putting in through the oscillator here, and I can vary the frequency. What you can see right now is that they are locked. If they weren't locked, by the way, it would just sort of be a mess. I'll show you what it looks like in a minute. Well, here, you want to see what it looks like unlocked? There you go. There it is unlocked. Okay? And what's happening is the oscilloscope is syncing or locking to the input waveform, and you can see the output one is doing weird stuff there. Okay, so that's not locked. There it is locked again. And a couple of things we can see. This is 100 kilohertz. That's right around the, this is very close to the free running frequency. Okay, and so what's the phase shift between these two signals right now? Just approximately. I mean, I don't want an exact number. It's about 90, and so guess what? It turns out this phase detector is exactly like the phase detector I described in the notes, which is to say that it operates symmetrically around 90. In other words, it operates from 0 to 180. Actually, this one doesn't operate from 0 to 180. I forget what, I haven't used one of these for a long time, but I believe the phase detector really only works from about 20 degrees to 160, but I can't remember. But it's something like that, but you get the idea. So in other words, what it does is it locks around 90 degrees. So right now, it's locked. It's very near the free run frequency. And what I can do now is increase the frequency here, or decrease it. So let's increase it like that. And you can see easily that it's quite synced. They're quite synchronized. In fact, whenever you see a pretty picture like that, they're synchronized. Now, check out the phase. What's the phase difference between the two now? Well, okay, 0 is a good, but maybe it's a bit positive, right? What does that suggest is about to happen? We're about to run off the end of our phase detector, right? In fact, I'm even surprised we got this far, to tell you the truth. Okay, so in other words, that's free running. It's about 90, and I keep this up. That's okay. There you go. So it just lost track. And in fact, what's interesting? There you go. So I got it back again. Okay, so it's well. See, actually, it's not bad. Goes almost up to maybe 10 or 15 degrees, and then it loses it completely. What's happening now is the poor thing is out of its range. If you remember, that phase detector has kind of a sawtooth picture. And so what's happening is this is a very, very complicated nonlinear system now, and it's jumping all around. And in fact, if you were to listen to this, which in fact we did, but we don't have time to do the longer version of the demo, it sounds actually just like the static you hear when you lose an FM station. And the reason that's what it sounds like is because that's exactly how an FM receiver works. It's nothing but a PLL. And when you are losing an FM station, all that's happening is a PLL is losing lock. That's what's happening. And so it's pretty random. Okay, so let me, another interesting thing you can see here, there's a lot of lore and so on with PLLs. For example, let me show you something. Here, once I'm locked, I can actually go way, 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 way up here, and then I lose it right sort of at the edge. Now what's interesting is if I decrease the frequency, I don't lock immediately again. I have to take it, to actually have it lock, you have to go reasonably far down. Hey, come on, you, there. And it only locks about there, right? So anyway, that's of course, none of this is in any way predicted by the linear model, of course, but there are more sophisticated analyses. Okay, so let's here we are again at about the free running frequency, the phase detector. So in fact, in your heads, when you look at this oscilloscope picture, you should be thinking this. You see this. This is what you see on the scope. You see that, and you see this. Okay? But you should be thinking this. And that's because it's just a phase error in between the two. Okay? So that's what you should be seeing there. Okay, so if I reduce the frequency, let's see that it happens on the other side. Let's go down. Now our phase now is approaching 180 degrees. I don't know, maybe 150. And we're close now to the point where we're about to lose it. Hey, come on. Ah, there you go. So in fact, we actually maintain lock almost all the way up to 180. Now I won't be able to regain lock actually until I pull it in a bit. Yeah, there you go. I'm pulling back. Okay, so there you see. And in fact, everything here is completely predicted by this this diagram here, almost everything except the difference in lock range here. For example, if you work out the DC, the steady state gain, or the steady state expression for theta error, you will get exactly this, directly from the linear analysis. Okay? Theta error is omega free minus omega n divided by g of 0 k det. In other words, you have to have enough phase shift to bend the VCO to match your input frequency. That's all this calculation is, or you can work out all the transfer functions and things like that. And so this is very, very interesting. It says that the error, the phase error, will actually decrease. It'll be 0 when omega n is omega free. Well, which means 90 because everything's offset by 90. And then it will decrease as omega n increases, and that's precisely what happens. Okay? So everything is predicted by this very nicely. And I think we're not going to do a, but there you go. There you see the whole lock range very nicely. Loses it, locks, and then loses it. Okay, so I guess I can't really think of any other fun stuff to do. Let me just mention a couple of other things about this one, and then we'll move on and we'll do a little bit of review and overview and stuff like that. One thing we don't have set up here that we could show you is it turns out that a properly designed phase lock loop works unusually well when you add noise, for example, to this top signal. In other words, I can add a very considerable amount of noise, and it will actually maintain lock. This is, in fact, why FM, for example, sounds better than AM, right? Because if I were to add little noises here, it will actually lock, and it'll lock even when the amplitude of the noise is on the same order of magnitude as the signal, which is actually kind of extraordinary, right? And certainly, if the ratio between the two is maybe 10 decibels or more, it'll lock perfectly. So that's an interesting fact about phase lock loops. But you'll be seeing these more at some point anyway. Okay, so I don't know, any questions about this or how it works, or I don't know what you can do with one, or
You don't have to like determine power.
what's that?
Power dissipation.
Oh, for this guy?
Yeah.
No, I don't know. Let's find out. You want me to tell you what it is? It doesn't say. It'll be here somewhere, but I'm sure it's relatively small. Actually, we started by hooking it up at. Oh, here you go. It's 670 milliwatts. No, that's the. You have to look it up. It depends on various things like the power supply voltage and all sorts of other stuff. But yeah, not a whole lot. It doesn't run that hot. It's slightly warm. That's all. So I'd say it's a quarter watt, something like that. Okay. All right. If there's no other questions about it, we'll just stick this stuff off to the side. I'll do it more fun here. I'll pull the input signal, and you get to see what happens to the thing. It loses it completely, and so on. Okay. So we'll quit. We'll quit here, and we'll go on to review stuff. So, I should say thanks to Leo for basically hooking all this stuff up. Yeah. Yeah, and actually having it work, which is an added benefit. It's great. Okay. Okay, back to the boring stuff. We'll do review. So I didn't put a whole lot of stuff together, but I did just put. I thought I'd just do one really stupid example. I'd work out one. There we go. And it's just a very, very simple one, and it's just to show you the types of things that we might ask. Actually, this is simpler than the types of things we might ask, but it kind of gives the idea. So here's a circuit. It's got an inductance and a capacitance. There's an input signal, and we could easily ask you to calculate something like, what's the transfer function from U to Y? And let's figure out what that is. We might ask, what are the poles, zeros, DC gain? What's the physical interpretation of the transfer function? I mean, does it make sense to you? How would you describe this output as a function of this input? What's the Bode plot of the transfer function, and what does it mean? What if the input were, for example, a pulse between, it's equal to -1 over the interval 1 between 1 and 2? What would the output look like? Again, assuming zero initial conditions, or maybe not assuming zero initial conditions. So these would be all very basic questions that you could certainly be asked. And let's jump in and look at some of those things. Oh, actually, let's see. Here we go. Let's first calculate the transfer function. Now, there's lots of ways we could do it. We could write down the differential equation that governs this circuit, okay? Which is, in fact, how we did it maybe for the first 2 weeks of the course. We could write down it would be a second order. We had that idiotic acronym, what was it, LCCODE or something like that, linear constant coefficient ODE. We could write that down, right? And then take Laplace transforms and so on. Or we could just look at this and use impedances. So we're going to use impedances. And if we use impedances, what you see here is actually just a voltage divider. Okay? And so you can write down almost immediately, 1 farad just from now on simply means 1 over S to you. 1 Henry means S in impedance. And so the transfer function we can just simply write down instantly is 1 over S divided by S plus 1 over S, because it's this impedance divided by the total impedance. And that's 1 over S divided by S plus 1 over S is 1 over S squared, 1 plus S squared. If I multiply through top and bottom by S, I get this. Okay, that's the transfer function. And the what's very, very important to do as you're doing all this stuff is to be basically on your toes and never, ever, ever turn off or leave off the part of your brain which is doing the intuitive analysis and the physical interpretation. Never turn it off. Okay, so you look at this. Don't just do that and move on. Let's think and see if it makes sense. What are the poles and zeros? Well, there's 2 poles. They're both at plus minus j. Here's the pole diagram. There's no zeros at all. Or what people say is no finite zeros or something like that. But there's just no zeros. Now, does it make sense? Does it make sense to you that this thing should have poles at plus minus j? What does that mean? If someone just walks up to you and says the poles of a system are at plus minus j, and they don't tell you anything else about it, what do you say? Yeah, oscillate. Yeah, exactly. Oscillate. You should think oscillation, oscillator, oscillatory response. If it's a vehicle, you should even get a little queasy. Of course, that depends on the frequency, I suppose, right? If it's, anyway, you get the idea. You should think instantly oscillation. Now, is there anything about this that suggests oscillation? Well, of course. If this were shorted, that's just an LC circuit. Again, that's a classical oscillator. So this is consistent. Not only that, what's the oscillation frequency? It's 1 over square root LC, which in this case is 1. So everything here is consistent. Now notice that if you do stuff like this and you make a sign error, it's gonna come up. You see what I'm saying? In other words, if you mess up here and you find out that the transfer function is 1 minus S squared, what would that mean to you? If the transfer function had been 1 minus S squared, what is that? 1 over 1 minus S squared. What does that mean to you? What do you think? Yeah, what would the poles then be for 1 over 1 minus S squared? Plus minus 1. And what do you think of immediately without further provocation? Yeah, you think of, well, the nature of the solution is that there's kind of a decaying component and there's a growing component. Okay? Well, to me, I don't know, if you thought of a decaying and a growing component and you saw this circuit, you should be profoundly suspicious. Okay? I mean, for one thing, you would have found a way to sort of generate energy from nothing or something like that. Okay? So that's why I actually want to emphasize that for a lot of this stuff, a sign error is not just an innocent sign error. And that's a warning to you on the final. A sign error is not an innocent sign error. If you're just doing algebra and it's pointless and meaningless, as for example you might do in a math class, a sign error is an innocent sign error. No problem. So you got a minus sign. Anybody, I make sign errors all the time. The difference here is that everything we write down means something. And so a sign error here means you're not thinking. That's what it means. So again, I just want to emphasize that this is the kind of stuff you want to be doing. Okay, the DC gain is 1. Does that make sense here? Sure. Because if everything were static, then for sure the inductor is just a wire and the capacitor is just an open circuit, and the transfer function from here to here would be 1. Okay, so again, That makes perfect sense. Let's look at a Bode plot of this transfer function. Well, if you work out what h of j omega is, it's 1 over 1 minus omega squared, and here's a completely bizarre thing. It's real, right? Because s squared is j omega squared is minus omega squared. You get 1 over 1 minus omega squared. And the first shocker is that the transfer function is actually real. The frequency response is real. Now, to be honest, that's something that could actually cause a little bit of confusion, because I'll tell you at least how it works in my mind. When I see resistors and I see things like that in amplifiers, then I think real impedances and real transfer functions and no phase shift. What is there to shift phases? Now, when you see inductors and capacitors, but these are precisely the things which shift phases. Not only that, these are pure imaginary. So your mind is set up and ready. You should be thinking about 90-degree phase shifts. That's what you should be thinking of. What is S? What's 1 over S? They're 90-degree phase shifts. Okay. So how it is that this thing could work out, that this signal would be in phase with that signal, is very interesting. Actually, it works because it's a ratio of imaginary to imaginary. That's why it works. In other words, that's pure imaginary, and the ratio is real. And in fact, you can kind of make some sense of that. It says if I put in a sinusoid here at a low frequency, this signal here is also a sinusoid, exactly in phase. The phase shift is 0, but it's a little bit larger. Well, that's strange. As omega here approaches 1, the transfer function grows. Okay, and right at omega equals 1, it becomes infinite. Now, again, does that make sense here? I think it does. If you have an oscillator and you drive it at a frequency which is just the oscillation frequency, in fact, what would happen then, by the way, in that case? What would it look like? You should know from Laplace transforms and things like that. You'd have 1 over 1 plus s squared. You would drive it at the same frequency, which would give you a Laplace transform, something like 1 over 1 plus s squared, and you'd have repeated poles. And so when you drive this circuit right at the resonant frequency here, the frequency, what will happen is you will get terms of the form t cosine t, right? Again, it sort of makes sense. It all makes sense. Okay? And in particular, when you drive at that frequency, you will not have a steady state sinusoidal solution. Okay? So anyway, this makes sense. Let's check a few other things. At high frequencies, what do you think? What does this circuit do at high frequencies? And don't give me any formulas. What does it do? What does an inductor do at high frequencies? No, it's the opposite of a short circuit. Yeah, it's the opposite. It resists. I mean, an inductor resists changes. So when you put high frequency voltage across it, very little current flows. Okay. A capacitor, on the other hand, is moving towards a short circuit. So whatever this thing does at very high frequencies, this ought to be low. And in fact, a real careful analysis would say that this signal here is not small. It's actually very small, and I mean that in the precisely formal sense. It means small squared. And the reason this signal should be small squared at high frequencies is two things are contributing to making this thing small. Number one, the inductor is going up in impedance and blocking the current flow through it. Number two, the capacitance is getting smaller and smaller in impedance, right? So, I mean, again, this is all complete hand waving, right? But the idea is basically there's two factors contributing to making this output small at very high frequencies. And let's see if that's confirmed. How is that confirmed here? Where in the algebra do you see that for large omega, the output of that thing is small squared? Where do you see it? Is it this one? This one? There it is. Okay. It's that 2, right? Yeah, it's this 2. It's that exponent, period, that tells you. Or over here, if omega is really large, this thing falls off like 1 over omega squared, right? So, okay, and if we were to plot the Bode plot, it would look something like this. The magnitude starts at 0 dB, that's 1. It rises, goes up to plus infinity at omega equals 1, and then up below that it falls off at 40 dB per decade. Okay, and again, this is a really stupid and simple example, and of course, you could treat this example in about 7 seconds. You just say, well, that's voltage divider rule. That's a transfer function. Next example, please. But I just want to give an example of I'm just slowing everything down, and I'm telling you the stuff that goes through my mind when I see this. And mostly it's just to catch my errors. It's just to catch errors and to make sure everything makes sense. And here's the phase plot. It's different from anything you've seen. It just says that it's 0, and then above this resonant frequency it drops down to minus 180. And you could predict that from here, right? That here's your little bead on the j omega axis, and you could work out the various angles here, like that, right? These various angles, and you can imagine the phase is obviously constant along here at 0, in fact. And then when you pop above here, this phase is still 90, and this guy switches from minus 90 to plus 90. The phase contributed by a pole that's in the denominator, it's negative, and so the phase reduces by 180 degrees. And sure enough, that's predicted, that's this. And you can also see it this way because this number for omega less than 1 is positive, and for omega less than 1 is negative, so that you can see again the phase shifting from 0 to 180. Okay, so you could probably say more about this, but I'm not sure what else you could say. I don't know, any questions about this? Say, what do you think the impulse or step response is going to look like? What's the impulse response of this thing look like? You figure that out? What's the impulse response? I don't remember. It's either what? It's either cosine t or sine t. It's one or the other. I don't know. Anyone remember? We could probably figure out what it is. It's cosine t, maybe. Okay. I'll trust you. It's cosine t. What's that? It's sine? I shouldn't have trusted. Okay. It's sine. Yeah. Actually, I know why it's sine. Anyway. Okay. So this is the impulse response is sine t. So if someone asked you in the time domain to explain what does this thing, how are u and y related, you would say that y is this thing convolved with u. And so, for example, does it have fading memory? No. No, in fact, the current output depends in a rather bizarre way on what the input has been all the way back. It remembers forever, right? It's not growing or whatever. If you put in a little blip or an impulse into this thing, its immediate effect is none of any kind. I guess that's 6 seconds, so that's 1.5. 1.6 seconds, say, after you put in a pulse, that's when you get your maximum effect. If you wait another 3 seconds, you'll actually find that your pulse has the opposite effect. Okay? So again, I'm just talking through what it means here, what this means. Okay, so that's the impulse response. And finally, we could solve this problem here, although it's actually quite boring to do. We could work out, for example, what would happen if a specific input went in, and that would be an exercise in Laplace transforms, for example. So here, this is a pulse, and I could work out what that is. That's a negative step. This is a delayed 1 second. That's delayed 2 seconds. You add them together, and this gives you a pulse. You can multiply this by that. I won't do the details because it's actually kind of boring. But this is the kind of thing where if you had to do this, and you might, sometime in the future, near future, you could do it. So anyway, that's the idea. You work out, and then you compute the inverse Laplace transform. Did partial fraction expansion on that, and you'd get this. And then you'd check all sorts of things. You'd check to make sure that the solution made sense. So, for example, in this case, the input, I think, looked like this. It's 0, and then at 1, between 1 and 2, it pops up. And the input should look something like that. And then it should, I don't know what it should do, but after that, it rings forever. Okay? It'll look something like that. I mean, if your input is not 0, for example, for the first second here, then, for example, we have a problem, and so on and so forth. So these are just the ways to do that. I'm rushing over this, but then this is just turning cranks and stuff like that. So, and I looked over the other stuff that we did, and there was actually only one thing I found. There was just a handful of little things that we didn't do, and I thought I'd mention a couple of them. Okay, here's what they are. For a transfer function, you have lots and lots of different data structures now to describe one. Okay, for a rational one, you have the residues and the poles. You have the zeros, the poles, and the gain. You have the frequency response, for example, in a Bode plot. You have the transfer function, like so. You have the step response and the impulse response. Notice the symbol clash here, right? But it's traditional. Okay? So these are all different data structures for describing the same thing, which is to say a convolution system or a transfer function or, well, the truth is you can think of any of these things as fundamental. They all describe the same thing. And what's important is for you to have both the specific skills of going back and forth between these, as well as some general ideas of how these things fit back and forth. So, for example, to take these two, how is H related to S? If I gave you the step response, what's H? It's a derivative. And if I give you H, what's S? It's the integral. Then there's interesting questions here. We have actually filled in the graph connecting these two, several of the connections. Some of the others we haven't, and you might want to do that yourself just to work it out. For example, we worked out, let's see, what have we worked out? We have worked out a nice way to figure the frequency response if you're given the zeros, the poles, and the gain. That we've worked out. And it's that beautiful graphical picture, right, where it's this graphical picture right here, right? The details aren't that important, but that's the graphical picture. Let's see, as another example, this one is easy to work out. The connection between the impulse response and the residues and poles is really easy because h of t is equal, in fact, to some rie to the pit. And here, I'm assuming, to make it simple, that the poles are distinct. They're not repeated. Otherwise, we have the t e to the pit terms and t squared and so on, right? So some of the connections here we've made very nicely, and a few of them we haven't. Let's see. Let me see. I think I worked out one. Here we go. Here's actually an interesting one. It's going back and forth between here and here. Going from zero pole gain to residues and poles is so this direction, that's partial fraction expansion. Okay? I guess going the other way is just algebra. But in fact, there's a useful geometric picture that we didn't give before. And so let me explain what that is. You remember from our formula for the residues that the right way to do, a simple way to do the residues is to plug in S equals, what you do is you take this expression here, you multiply by S minus P, the pole you want to check, and then you plug in S equals P. And you get a formula that's just an explicit formula, which is just this. And it's K times the product of Pi minus Z1, Pi minus Zm. And here, it's the product of all the differences of poles, except you've removed the one you wanted to take out. This is just a formula for doing what you do anyway when you do partial fraction expansion. This is the formula. But if you look at it long enough, you'll realize it tells you about the magnitude of a residue. Magnitude of a residue depends on the product of the distance from that pole to all the zeros, divided by the product from the distance of that pole to every other pole, which is kind of interesting. So for example, if I had a pole here, right? And I ask, what's the residue of this pole? Well, you'd have to calculate this distance and this distance and this distance, and you'd multiply by that distance, which is very small. So the residue would be very small. Okay? This actually makes perfect sense if you think about it, because if I walked up to you and I said, here's my transfer function, and I've got this pole and this zero like that, you'd say, well, they almost cancel each other. And in fact, that would come out in the time domain because the residue of this pole would be really small. And so whether or not you could neglect it depends on how small that residue is or something like that. So that, again, makes sense. Okay, so this was one connection. I think we didn't explicitly say it, although it's, I guess, these are kind of obvious. And then finally, there's all the qualitative connections between these. And these I hope you've got. First of all, it's good to have the qualitative connections because it helps check as you do actual calculations and so on. So for example, burned into your neurons should be the idea that if there's lightly damp poles, in other words, if you have poles like that, this should mean all sorts of things. For example, on a Bode plot, on the magnitude plot, you should expect a big peak in the frequency response. And that makes perfect sense. What it says is if you feed a sinusoid into that system near these frequencies, the output, you're going to have a very big response at the output. You should also realize that this means that there'll be a rapid phase shift near that frequency. In the time domain, it means, for example, in either the impulse or the step response, it means you're going to see a lightly damped decaying sinusoid. So your impulse response might look something like that. Your step response could well look like something like this. Okay? And the oscillation frequency is going to be omega 0, and the decay rate is going to be related to sigma 0 here. So these are the ideas. And in fact, this should be burned in your head only at this level. In other words, it should not be... I mean, these are all vague, right? And this is just these are just ideas. Okay, well, I guess, let's see, maybe there's some questions or something like that. I mean, that kind of covers the holes I found. There actually weren't that many holes in what we did, so. You're right, right here. That shouldn't be there. You're absolutely right. Yeah. Right. Okay. Well, let's see. In that case, let me take 1 minute to thank Leo and Jessica for everything. Huge amount of work with all the homeworks and exams and all that kind of stuff, and the demos, as well as our SITN operator, who I think actually is even enrolled in the class. So, especially with all the fancy stuff with the oscilloscopes up. And guess what? We have these to do. So I need a volunteer. Who's going to volunteer? I don't know. EE department. I think if you just walk into the EE department and wave this around, someone will find you and tell you what to do. We have a volunteer. No, it's in Godzilla. Yeah, I'm sure it's everybody's favorite place. Okay, so I'll quit here, and you get these. So.